Imagine you have a machine that rings a bell whenever something goes wrong. It works great at first, but then the weather changes, or the gears wear down a bit. Suddenly, the bell rings even when everything is fine. That is what we call a distribution shift. Your model thinks the new normal is a mistake. We need a way to teach the machine to adjust its expectations on the fly without breaking what it already knows. That is what test time adaptation is all about. Look at these graphs. In the top left, you see the training data in blue and the test data in orange. They do not line up. That is the shift. Now look at the bottom. The gray spikes are the scores. Because the test data moved, the scores jump over that dashed line even for normal behavior. The model is yelling, "Fire!" Just because the room got a little warmer, it is a failure of the pre-trained detector. It cannot distinguish between a real problem and a simple change in the environment. How do we fix this? We do not just retrain everything. That would be an expensive mess. Instead, we use CANDI. It looks at the scores and asks, is this spike a real anomaly, or does it just look like one of those tricky normal cases we saw before? It mines for false positives. If a new data point is close to a known hard normal case in the model's inner map, we use it to learn. We are picking the most useful examples to show the teacher rather than just guessing. This is the Sana module. Notice it is just a little piece added to the front and back of the big frozen model. It uses convolutions to see how things change over time and attention to see how different sensors talk to each other. By keeping the main brain frozen and only tweaking these small layers, we avoid forgetting what we already learned. It is like putting a new pair of glasses on a student instead of performing brain surgery. They see the new world clearly without losing their old memories. These are RIOC and precision recall curves. You want the lines to stay as high and to the left as possible. See the black line? That is CANDI. It stays way above the red line, which is the model that did not adapt. Even when we use fewer samples, what the authors call CANDI hard, the performance stays high. This tells us that picking the right samples is more important than picking a lot of them. It shows our little adaptation trick really works to stop those false alarms. We did not just play with toy data. We used real stuff from water plants and server clusters. The results were clear. Even when the pre-trained model was failing, like on the SMD dataset, Gesta pulled the accuracy way up. What is really neat is how efficient it is. It only needed a tiny fraction of the data to get these gains. It is like a student who only needs to see a couple of hard examples to understand the whole new lesson. That, ladies and gentlemen, is a real learning efficiency. So to recap, real-world data is messy and changes. If you have a static model, it will eventually fail. CANDI gives us a way to keep models fresh by carefully picking which samples to learn from and using a smart small module to handle the updates. We get a system that stays accurate without getting confused. It is a simple, elegant solution to a very common problem in machine learning.